Hey everyone, we're now in section 8. We're talking about complex numbers. Our discussion of complex numbers are going to begin with the imaginary numbers, truly imaginary numbers. So that means that we're going to be looking at the square root of -1. Now amazingly, the square root of -1 can be defined to be a number, and the mathematicians who showed that that worked decided to call that number I. So there's two ways of writing this. You can think of the square root of -1 becoming I, but that's the same thing as saying that I is the square root of -1. So whichever side you're on, they are equivalent. We're basically defining the square root of -1 to be I. Now the moment we have that, we've got a true statement. That's the definition. So we can square both sides just like you would with an algebraic expression, and if you do that, you get I squared equals -1. The square undoes the square root. So basically I is a number that when you square it, when you multiply it by itself, you get a negative. Now there only needs to be one number like this, and the reason that that's true is illustrated with our first example, the square root of -81. This doesn't require another imaginary number. I will do just fine. And the reason for that is that multiplication inside of a radical can come out. So the trick here is to think of -81 as two numbers being multiplied together, as -1 times 81. So if we can take that negative away, if we can make it a separate factor, then that will give us an I, and then of course the square root of 81 will give us a 9. So here's that happening. In the first case, we've got the multiplication inside the radical, and in the second case, we've got the multiplication outside the radical. Multiplication goes inside and outside radicals. Of course, that does not work for addition and subtraction. It does work for division. The moment that we separate this into two things, we see the square root of -1. Well, that pops out as an I. So there's that same I, the square root of -1, and we're multiplying that by the square root of 81, which is just 9. So this works out exactly the way you'd expect, as 9I. Now, what can we do with that? Well, what happens if we put a negative sign out front? So in our next example, we've got the negative, or the opposite, of the square root of -50. Now, I cannot bring that negative inside, because basically that would be like bringing an I inside. So I'm going to leave the negative out front, and I'm going to simplify the square root of -50. So that means there's going to be a negative following us along. There's going to be a negative inside the radical from the -50, and then we're going to simplify the 50. So let's follow this through. So here's the negative out front, just following us along, just all ready to be part of the answer. And then we're going to do the same thing to -50 inside the radical that we did to the -81. We're going to break the negative off. We're going to use the fact that multiplication inside comes outside, and that will give us an I out front. So now we've got a negative and an I out front. Now 50 is interesting because it contains a perfect square as a factor, namely 25. It also contains a 2 as a factor. Now the 25 inside of the square root, because it's a perfect square, is going to give us a 5. So when we collect all these things up, what do we got? We've got a negative, an I, a 5, and a square root of 2. So all of those things together, negative I, 5, square root of 2. That's exactly the same number, just written in a different way. Now, using this definition, we can kind of start playing with it. The first thing that we did with the definition is we squared both sides, and we saw that I squared equals -1. So now we're asking the question, what is the opposite of I squared? What happens when I change its sign? And so for that, we're going to say, well, I squared is, by definition, -1. We've got a negative sign out front that's following us along. So basically that's saying that we've got two negatives now after we simplify, and of course a negative times a negative is a positive. You can also say this as the opposite of -1 is 1. Now, that's interesting in itself. We've got back to positive 1. But take a look at this. Here's a question that just seems so wrong. In Math 100, we said, and I tell my Math 100 students this, that a negative exponent does not make a negative number, because in Math 100 you don't have complex numbers. Now that we do, let's take a look at what happens if I take a number as strange as I and raise it to a negative power. Now it's going to do exactly what you expect. That negative exponent is going to tell me that the base is in the wrong place. It should be in the denominator. So the first thing you're going to see is 1 over I. So there's our 1 over I, exactly like you'd expect. It's telling me that the base is in the wrong place. Now that's fine, except I have to rationalize this. Remember, I is a radical. So I'm essentially saying 1 over the square root of negative 1. And I'm not allowed to have radicals in the denominator. So I'm going to multiply by a form of 1. I'm going to get rid of the I in the denominator by squaring it, by multiplying I times I. And of course, I times I is I squared, and I squared is negative 1. Now, the price we pay for that, if we want to multiply the denominator by negative 1, is we also have to multiply the numerator by, multiply the numerator by I. So 1 times I is I. Now, take a look at what we've got. We've got an I in the numerator, but all we've got in the denominator is a negative 1. That's just going to change the sign. So as weird and counterintuitive as it looks, a negative exponent does give us a negative number when we're talking about complex numbers. So there you go. There's a quick introduction to imaginary numbers. Now let's start to do arithmetic with imaginary numbers, not just simplifying them, but doing stuff with them. In the first two examples, we're going to be multiplying. And multiplying complex numbers, multiplying imaginary numbers, may seem tricky initially because there's only one way to get the right answer. And that's not often the case in mathematics. In mathematics, it's usually the case that you can get the right answer lots of different ways. If something's a true statement, you can use it to get the right answer. So you might say, let's take that multiplication that's outside the radicals and bring it inside the radicals. You might say that. The problem is that would give you negative 3 times negative 3 inside of the radical. And a negative times a negative is a positive. That's the square root of positive 9, which would pop out simply as 3. So be very clear that you see that what's happening now is a special case. It's the one way through to get the right answer. Because really what's going on here is we can't lose sight of what this question is asking us. This question is asking us about complex numbers. It's not asking us to do multiplication. It's asking us to believe that something like the square root of negative 3 really exists, that it has meaning. And if it does have meaning, then it is an imaginary number. So the first thing we're going to do is we're going to simplify both of these, just like we did before. So notice that the negative 1 as a factor inside of each of these radicals comes out as an I. So we've got I root 3 in both cases. They're the same number. So we've got I root 3 times I root 3. Multiplication is commutative and associative, so I can take those two i's together and get an I squared out of them. Similarly, I can take the two root 3's together and get root 3 squared. So just rearranging the order of that multiplication. Now I squared is by definition negative 1. So what have we got here? We are in a few seconds going to see that gives us a negative, and the square and the square root on that 3 are going to undo each other and give us negative 3. So there's the negative 1 times the 3, which gives us negative 3. Notice that that is a negative 3, and that's how I can tell just from your answer that you did this process correctly. That you acknowledged that at the beginning you had complex numbers, you had imaginary numbers, and so those i's had to come out. And it's those two i's, when you multiplied them together, that I squared, that gave you the negative. So just by looking at the answer, I can tell you used the correct procedure. Okay, let's work through this again with another example. Here is the square root of negative 6 times the square root of negative 5. And we're going to do the same thing. We're going to simplify that. The two i's come out as an I squared. And then we're going to multiply the 6 times the 5. Of course, 6 times 5 is 30. that I squared is going to do exactly what it did before. It's going to become a negative 1. And that negative 1 times the square root of 30, we're going to write that just as negative square root of 30. And again, notice that I can tell if you use the procedure correctly because I can see that there's that negative out front. So that's pretty heavy. When you're forming the product of complex numbers, you've got to remember and acknowledge that they are in fact complex. Now let's take a look at the quotient. So this next example, we're dividing two imaginary numbers. I know that because we're taking the square roots of negative numbers. Now, there's lots of ways to do this, but I'm going to do it in exactly the same way that I did the previous two. I'm going to simplify the numerator and simplify the denominator. So the first thing that I see on the numerator is that we've got an I upstairs because we've got the square root of negative 1, and we've got an I downstairs because we've got the square root of negative 1. Now, those two i's aren't not being multiplied, they're being divided. And a number divided by itself, except 0, is 1. So those i's are going to go away. They cancel. Now, we're going to simplify that. There's lots of ways of simplifying this, but I noticed that 3 goes into 75. In other words, that division actually helps us. So I'm going to take the division that was outside, and I'm going to bring it inside. Now, I'm doing that because I see that this will help, that 3 actually does go into 75. It goes into 75 25 times. So now we've done that division inside of the radical, we can now actually take the square root. And the square root of 25 is 5. Notice there's no negative here, and that's because the two i's canceled. So when we're forming a quotient, when we're dividing complex numbers, or in this case purely imaginary numbers, the i's are going to cancel. When we multiply, and this is an important distinction, the i's don't cancel. They actually give us a factor of negative 1. Okay, now all this is good, but we need to remember where we've been. And where we've been is that we already know that sometimes you can take the root of a negative number. And you can do that if the index is odd. So here are two cube roots. And so before we do anything, just look at that and convince yourself that this has nothing to do with imaginary numbers. And the reason for that is the cube preserves the sign. That's the way we say it in Math 100. Basically, it means that if you cube a negative number, if you multiply itself by itself 3 times, you get a negative number. It keeps the sign. So the cube root has something to go back to. That's how we say it in Math 100. So in this case, this is a Math 100 question. All we're asked to do here is simplify this. There are no i's as a part of this. Now I can do the same thing, and it's probably useful to do the same thing, and that is to break off the negative. So notice here I made a bigger fuss than usual about the fact that the 18 that's left behind is positive, so I've got a plus sign there. You don't need to show that, but I'm basically showing that I'm taking out the cube root of negative 1. And we just talked through that. The cube root of negative 1 is negative 1, because when you cube a negative, it stays negative. And then I pointed out that when we get the negative out of that 12, that negative 12 in the second cube root, we've got a positive left behind. Now, those two cube roots of negative 1 are not going to give us i's, they're going to give us negative 1's. So I'm going to group those together. So here they are. I took both of them and put them together. So there's the negative 1 from the first cube root of negative 1 and the second negative 1 from the second cube root of negative 1. And that's going to go away. A negative times a negative is a positive. And what's left behind, I showed all the factoring because every once in a while it's good to do that. 18 is 3 times 3 times 2. So there's the 18. And 12 is, so there's our 12, just following everything along. And 12 is 2 times 2 times 3. So you can work through this. 2 times 2 is 4. 4 times 3 is 12. Now, all of this is inside of a cube root. And what does that mean? That means they come out 3 at a time. And look at how lucky we are. We've got 3 factors of 2, some from one of the radicals, some from the other. And similarly, we've also got 3 factors of 3. So when we take them out of the cube root. 1 factor of 3 comes out, 1 factor of 2 comes out. Remember, we're still multiplying. We were multiplying to begin with, and we're still multiplying. We're going to multiply that 2 times the 3, and that's going to give us an answer of 6. Okay, now is a good time to talk about complex numbers and how they're different from the imaginary numbers that we were talking about earlier. So the first thing we should probably talk about is the fact that a complex number like 3 plus 5i has 2 parts. The 3 is the real part, that's the real number, and the 5i is the imaginary part. So that's how these words fit together. If I take a purely imaginary number like 5i, and I add a real number to it like 3, I get a complex number. So here are 2 complex numbers, 3 plus 5i and negative 7 plus 2i. And we're asked to add them. Now, you might say it would be almost easier to do this if we didn't remind ourselves of what I is. Just think of I like an X or an A or a Y. They're just things that make the 5i and the 2i into like terms, and the 3 and the negative 7 into like terms. So the first thing that we can do here is simply collect the like terms. So here's the 3 and the negative 7 next to each other. We're using the associative and commutative properties of addition. And here's the 5i and the 2i next to each other. In other words, we've got the like terms together. So we're going to do exactly what you expect. 3 minus 7 is negative 4, and 5 plus 2 is 7. So here's another complex number. The real part is negative 4, and the complex part is positive 7i. And that's our answer. We've added these. Now, the moment you see how this goes, you realize how easy this is. This is just combining like terms. So you might say, well, how would this change if we did subtraction instead of addition? And it definitely would change. Because remember, when we subtract, those parentheses are telling us that we're subtracting that entire complex number, not just the 2, but also the negative 5i. So you can think of that subtraction as distribution. We're going to distribute that negative 1 into the 2 and the 5i. So that'll change both of their signs. Now, the parentheses on the first complex number don't really need to be there. Notice that that negative 3 minus 5i stays negative 3 minus 5i when we perform the subtraction. But when we distribute it, the 2 becomes a negative 2, and the negative 5i becomes a positive 5i. And we're going to do the same thing we did before. We're going to combine like terms. So the 2 like terms that are real here are the negative 3 and the negative 2. So negative 3 minus 2 is negative 5. And what's kind of interesting about this problem is notice what happens to the imaginary parts. Negative 5i and positive 5i cancel out. They end up to be 0i, and 0 of anything is 0. So this is no more nor less than negative 5. So with that, that's really the only 2 cases when we're combining. Either we're adding them, we just combine like terms, or we're subtracting them, and we distribute and then combine like terms. We're now multiplying, and this happens exactly the way you'd expect. We've got 2 purely imaginary numbers, 5i and negative 7i, and we're multiplying them. And you might think of this as having 4 parts, the 5, the I, the negative 7, and the I. So we're going to use the associative and commutative properties of multiplication. We're going to multiply the 5 times the negative 7, and we're going to multiply the I times the I. Positive times a negative is a negative. 5 times 7 is 35, and I times I is I squared. Now, you might say that I squared doesn't need to be there because I squared is no longer an imaginary number. I squared is negative 1. And if you multiply a negative number like negative 35 by negative 1, the negatives go away, and we're left with positive 35. So just multiplying each piece separately. You can think of 5i as being one imaginary number, or you can think of it as having 2 pieces, the 5 times the I. Now let's move on to a question where we actually have to do some distribution. This 6i is being multiplied into the sum, negative 2 plus 3i. So that's going to require some distribution. So we're going to multiply the 6i times negative 2, and we're going to multiply the 6i times 3i. And when we do that, a positive times a negative is a negative. 6 times 2 is 12, and of course there's that I. Similarly, when we multiply the 6i into the second term, a positive times a positive is a positive. 6 times 3 is 18. I times I is I squared. Now, negative 12i really is an imaginary number, but 18i squared isn't, because I squared is, by definition, or pretty close to the definition, negative 1. That's going to make that 18 into a negative 18. Notice how we put the I at the end. We're still treating it like a radical. Now, here's a question that's got a lot more going on in it. Here's a complex number. Remember, that means it has a real part, the 3, and an imaginary part, the 5i, times another complex number. Now, again, I think it helps, at least in the initial parts of this problem, to think of this as a problem you've already seen. Imagine this is like 3 plus 5x times negative 7 plus 2x. In other words, imagine the i's were x's, and you do exactly what you'd think. You'd FOIL. So we're going to do that as well. When you've got a binomial times a binomial, these aren't binomials, but they behave just like them. They've got two terms. They're two-dimensional numbers, so we're going to FOIL them just like we would a binomial. So FOIL is just a mnemonic to make sure that we get every pair from the first to the second, first, outer, inner, last. So here we go. Here's our firsts. When we multiply 3 times negative 7, we get negative 21. When we multiply 3 times 2i, that's the outer pair, we get 6i. When we multiply the inner pair, that is 5i by negative 7, a positive times a negative is a negative. 5 times 7 is 35, and there's our I. And last but not least, when we multiply the 5i times the 2i, 5 times 2 is 10, I times I is I squared. So there's our FOIL. But one of the things that we should definitely deal with right now is the fact that that positive 10i squared is actually a negative. Remember that I squared is negative 1. So it, that is the negative 10, is a like term with the first term, the negative 21. So we're going to combine those. If you owe someone $21 and you owe someone else $10, you owe a total of $31. And of course, we're going to combine the imaginary parts as well. We've got 6 i's and negative 35 i's. Looks like the negative is going to win by 29. So we've got a complex number as our answer, and that number is negative 31 minus 29i. Let's do another one of these. We're going to do it exactly the same way. We're going to notice that it looks an awful lot like a binomial, a two-termed polynomial, but in this case a two-dimensional number. We're going to FOIL just like we did before, and we're going to get the same 4 terms, the first, outer, inner, and last. So that first is the negative 3 times the positive 2. The outer is the negative 3 times the negative 5i. A negative times a negative is a positive. Inner is negative 5i times 2. A negative times a positive is a negative. 5 times 2 is 10, and we've got that I. Last but not least, notice that the negatives, just the negatives in the negative 5i times negative 5i give us a positive. A negative times a negative is a positive. 5 times 5 is 25, and then I times I is I squared. So this number looks positive again, but it is not. The I squared makes that positive 25 into a negative 25. So just like the previous example, that means that it is a like term with the negative 6. So when we combine like terms, we're going to get negative 31 plus 5i. Our next question looks really similar to the one that we just did. It is, or at least it can be done, as a FOIL question. In a few seconds, I'll do this using the shortcut that'll remind you of factoring a sum and difference. Here's a FOIL question, and I say that because when you multiply a number by itself, you've got two of those factors. So negative 7 plus 2i times itself. So we're going to FOIL this. There's first, outer, inner, last, so make sure you can go through and check that. The positive 49 comes from negative 7 times negative 7. The outer terms are a negative 7 times a positive 2i. The exact same thing, but now they're the inner pair. And that last but not least, a positive times a positive is a positive. 2 times 2 is 4. I times I is I squared. And just like before, the negative sign comes from the I squared. I squared is a factor of negative 1. We clean up what we've got. That is the real parts. 49 minus 4 gives us 45. And then when we take those two purely imaginary parts, the negative 14 i's, we've got two of those. Negative 14 minus 14 is negative 28 when we're counting the i's. Now at this point, you're probably just overloaded with arithmetic. Just the kind of a reminder of polynomials and foiling and combining like terms. So in this next example, I really want you to see that something big is going on. And the moment you see this, you'll remember exactly what this is. This is a Math 100 idea in the context of Math 120. This is the conjugate. So before we do anything, I want you to see that there's more than just arithmetic going on here. Because the moment I say conjugate, you're thinking to yourself, well, I remember how that goes. That's how we got rid of radicals, well, in particular square roots, in denominators in Math 100. The conjugate is a powerful thing. So if up to this point you were thinking about arithmetic and polynomials and just getting an answer, we're now trying to turn the tables on these questions and say, I wonder how I could get rid of a complex number, how I could get rid of an I. And that's a heavy-duty question. That's an important question. Notice that these are almost the same. The first term is, or the first pair is a sum, and the second pair is a difference. There's only one sign changed from one to the other. They're not opposites, right? This is not an opposite. We didn't change the sign on 5. They're positive in both cases. This is the conjugate. And the conjugate is powerful. It's powerful because it gets rid of I. So if you're thinking to yourself, yeah, I remember doing this with radicals, I mean, now might be a good time to remind yourself that I is a radical. It's the square root of negative 1. So we could FOIL this, but I want to remind you that when you're multiplying what looks like a binomial times another binomial, the only thing different is that one is a sum and a difference. This becomes a difference of squares. So remind yourself that from Math 100, that this is the first base, 5 squared, minus, and it has to be minus, that's why we can factor those difference of squares as a sum and difference, minus the second base, 2i squared. Now, we're going to actually do that, right? So we're going to square 5, that's going to give us 25. We're going to square 2, that gives us 4. And we're going to square I, that gives us I squared. Okay, now here's the really cool part. That I squared is going to become a negative 1. And I'm going to show that in all of its detail. There is the same thing, the 25 minus 4, but the I squared has become a factor of negative 1. Notice this is no longer has an imaginary part at all. A negative times a negative is going to give us a positive 4. So we're going to take that 25 and add 4 to it, and we get 29. That's why this is called a conjugate. It works the same way that it worked in Math 100 for the conjugates when we were getting rid of square roots. Interestingly, and a little bit beyond the scope of this class, from the rules for factoring cubes, you know what the conjugate of a cube root is. Just saying. Now we're going to do some division, and of course division is just like division with radicals. So I'm going to remind you of that when we divide complex numbers, we're really rationalizing. So when you look at these two questions and you say to yourself, well, what's wrong with them? I mean, why aren't they an answer themselves? I mean, 5 divided by 7i looks like a perfectly fine not only question, but answer to that question. So remind yourself that the problem is the I. And the easiest way to think of this in the context of Math 100, the previous course, is to say to yourself that I is the square root of -1. The square root. There's a radical in the denominator, exactly where it shouldn't be. So we're going to rationalize. And when we rationalize, we're going to be very strategic. The 7 is not giving us any trouble. We're allowed to have 7s in denominators. It's the I down there that we don't want. So when we multiply by that form of 1, we want to multiply by something that makes an I go away. And the best way to make an I go away is to multiply it by another I. So we have I squared being -1. So we're going to multiply numerator and denominator by I. Up in the numerator, that's going to give you exactly what you expect. 5 times I is 5I. Down in the denominator, 7I times I is 7I squared. And this is good because even by the next step, 7I squared becomes -7. Now, that's just awkward. We don't write our fractions containing negative signs. So we want to take that negative out front. That's easy enough to do, just to say that this is a negative number. So that negative sign's out front, -5I over 7. So we divided, but of course, just like with radicals, dividing means to rationalize. Now, a very similar question is next. The only thing different is that the arithmetic, the algebra, is going to be a little bit more difficult because we're going to have to distribute. And the reason I know we're going to have to distribute is because I see subtraction in the numerator. And remember, fraction bars are grouping symbols. So when we multiply numerator and denominator by I, just like we did before, we're going to do exactly the same thing. We'll have a little bit more work in the numerator. Now, downstairs, you get exactly what you think. 3I times I is 3I squared. Bye-bye I. That's about to become a -1. The numerator, we're doing that distribution. So I is being multiplied by 2, giving us 2I. I is being multiplied by -5I to give us -5I squared. Now, both of those I squareds have to be simplified. So in the numerator, the I squared gave us a -1. And the same thing downstairs in the denominator. The I squared gave us a -1. So in the numerator, -1 times -5 is about to become +5, and that's fine. But in the denominator, we've got a -3. Just like in the previous question, we don't want negative signs stuck inside of fractions. We're going to bring it out front, and there's our final answer for that one. Okay, the last page of our discussion of complex numbers. So, by some measure, this first example, 2 over 1 minus I, is kind of the crescendo of what we've been learning. It draws on a lot of Math 100 ideas. And the biggest of those, of course, is the conjugate. It would be great to just be able to multiply the denominator by I. And we will be able to do that in the next example because all we've got down there is an I. So that's a much simpler question. This is very clearly a Math 120 question. Look at that denominator. If I multiply by I have to distribute, which means the 1 gets an I. Maybe the I squared goes away, but multiplying by I does not get rid of that difference, 1 minus I. So the first thing I have to do is multiply by the conjugate. And the conjugate of a difference is a sum, so there's our conjugate downstairs. And what I mean by that is the conjugate of subtraction is addition. So we're just changing one of those signs. Notice that the 1 is positive in both cases. It's only the I that changes sign. Now downstairs we could FOIL. If you do that, the middle two terms, the outer and the inner, are going to go away. But I'm going to use the definition of the conjugate. It's going to give me a difference of squares. In the numerator, I'm going to distribute, and then I'm going to rapidly decide that I shouldn't have distributed because I see where the denominator is going. Now, not a lot's going on with that first square. 1 squared is 1, but quite a bit's going on with the second squared. I squared is -1. And if you're thinking to yourself, oh no, this is going to be 0 because 1 minus 1 is 0. This isn't 1 minus 1. This is 1 minus -1. And so in the next case, we'll see exactly what's going on. That's 1 minus -1 down there. So that's about to become a 2. And the moment I spotted that, I thought, oh, I shouldn't have distributed that 2 into the numerator, so I factored it back out. Because in the next step, we're going to see that those two fine 2's actually cancel. We don't have to make any comment about that because 2 divided by 2 is just another name for 1. And here's our final answer, 1 plus I. And you might say, well, okay, we perform the division. I mean, really that feels like rationalizing to me. You can call it division, but it certainly gave us a nicer answer than what we started with. And really, this question is tops in terms of making sure that Math 120 is working for you. So look over that example a few times. Remind yourself how to get the conjugate. You just take that, whatever it is, whatever the sign is, in this case it's subtraction, and you change it, in this case, to addition. You've got to have one of each so that the middle two terms go away when you FOIL, so that when you use the shortcut, you just get a difference of squares. So the key word there is conjugate. Now, when I look at the next example, this one's going to be so much easier because all I've got downstairs, remember that's why I'm doing what looks like division, because there's a radical. Remember, an I is a radical. It's the square root of -1. There's a radical in the denominator. So I'm going to multiply by a form of 1, but it's not very fancy. It's just I over I. It doesn't have to be fancy. Anything fancier would be crazy. All I've got downstairs is an I, so I multiply it by another I, and voila, downstairs is an I squared. So make sure you can see that. Remember, multiplying fractions is the easy one. Just multiply the numerators together and multiply the denominators together. That I squared downstairs is about to become a -1. Now let's look at the numerator. Remember that a fraction bar is a grouping symbol. So imagine parentheses around the 3 plus I when we multiply it by I. What I mean by that is we're going to have to distribute. And when we distribute, 3 times I is 3I, and I times I is I squared. So we've got a little cleanup to do now because both of those I squareds become -1s. Now, division by a -1, well, we could bring the negative out front, but then there'd be nothing left and would have the parentheses because we've got a fraction bar. We're basically saying divide everything by -1. That's exactly the notation that we'd use to say change all the signs. And when you do that, we're going to change the sign on the positive 3i. That's going to give us a -3i. We're going to change the sign on the -1, and that's going to give us a +1. And there's our answer. A lot nicer, at least to my eyes, than the question that we started with. Now, one of the fascinating things about I is it's very much like -1. And that makes sense because it's the square root of -1. But what I mean by that is it has a pattern that repeats. -1 to the first power is -1. -1 squared is +1. -1 cubed is -1 again. And you can quickly see the pattern. 1, -1, 1, -1, 1, -1. I has a pattern like that as well. It kind of goes around in circles, never breaking out of its routine. So that's what we're going to talk about now, is how to deal with higher powers of I, which is another great Math 120 question. So we're going to just look at some powers of I until we see that pattern, just like the pattern with powers of -1. -1, 1, -1, 1, -1, 1. It's going to be a little bit more exciting because, of course, we've got i's, and i's are radicals. So the first and slightly obvious thing to say is that I is I to the first power, and that's equal to I. Now there's really no information in that. That's true for anything. X is equal to x to the first power is equal to x. But it does remind us what happens when our exponent is 1. When we've got I squared by definition, or at least real close to it, is -1. Now take this equation that we just had. I mean, that is an equation. We have I squared equals -1, and let's make it into I cubed. That means multiply both sides by another I. And when you do that, you get on the left side, well, I squared times another factor of I is I cubed. And so you might say, well, what happens on the right side? Well, on the right side, we're going to take that -1 and multiply it by I, and that'll give us -I. And so we can do that same trick again. To find I to the 4th power, our next question, we can simply take the previous equation and multiply both sides by an I. And of course that's going to give us an opposite, a negative sign that is, and 2 factors of I. That's going to give us 1. 1 because it's the opposite of negative 1. Now, message repeats at this point, because if I take this equation, I to the 4th equals 1, and I multiply both sides of it by I get I to the 5th. But I'm also multiplying I times 1, which is taking me back to I. So I'm starting to see that repetition. In other words, this is I to the 5th is the same as I to the 1st. We're seeing that same kind of pattern that we saw with powers of negative 1. Negative 1, 1, negative 1, 1, negative 1, 1. Of course, this takes 4 to cycle through. There's an I, a negative 1, a negative I, and then a 1 before that message repeats again. Well, let's make sure that this works. Let's take the equation, I to the 5th equals I, and multiply both sides by I to figure out what I to the 6th is. So when we multiply both sides by I, we're multiplying I times I, and that's negative 1. Yep, that fits the pattern. And we're going to do the same thing again. Let's take this equation, I to the 6th equals negative 1. Multiply both sides by I. That's going to give us I to the 7th on the left side. And I to the 7th equals a negative 1 times an I. Yep, there it is, negative I. And then if we take that equation and multiply both sides by I, guess what? We get back to 1. So that message does repeat. That pattern does hold. I, negative 1, negative I, 1. And then again, I, negative 1, negative I, 1. So we can show this the way we show a clock. In other words, this takes us around in circles. So here's such a clock. We can start with something perhaps even easier to deal with, and that is the fact that anything other than 0 to the 0th power is 1. So I to the 0th power is 1. And then we can say, well, how does this look? There's that 1, the start of the pattern. I to the 1st is just I. And at this point you might say, well, this is not really telling me that much. The first is a property of exponents with 0. The second is a definition of an exponent of 1. The third, when we've got I squared is negative 1. There is a little negative sign there. Make sure you see it. I kind of shoved it up next to the 1, but there is a negative sign there. And then I cubed is negative 1. And if we multiply by another factor of 1, if we say, let's talk about I to the 4th, you might as well say we don't have to worry about talking about I to the 4th. It's the same as I to the 0th power. And the moment you see that pattern, that idea that looks a little bit like a clock, but instead of with 12 hours, it's got 4 numbers. 1, I, negative 1, negative I, 1, I, negative 1, negative I, 1, and around it goes. The moment you see that, you realize that you don't really need higher powers of I. In other words, 0, 1, 2, and 3 are all you need to worry about. Because if you had I to the 4th power, you can quickly convince yourself that I to the 4th power is the same as I to the 0th power, is the same as I to the 8th power, is the same as I to any multiple of 4. So let's use that fact. So here are some questions with I raised to just big exponents, just to see what we get. Now, one of the things that's going to happen here is that we're going to see I to the 0th power. And we've already seen this, and I've said any number other than 0 to the 0th power is 1. And that's cool, and that's actually why we accept I into the world of numbers, because it behaves like numbers. It works the same way as the other numbers we've got. So when we look at I to the 72nd power, that looks grand and very worthy of a Math 120 class. But we remind ourselves that really all we have to worry about is 0, 1, 2, and 3. In other words, if we had 4, if we had 12, if we had 40, I'm just mentioning multiples of 4, all of those would take us back to 0. Well, that's exactly the definition of division. We're saying, hey, get rid of all the multiples of 4. You can go around as many times as you like. And remember, going around means going 4 times. So we're going to divide by 4, and we're going to see what we get. And what we're interested in is not the quotient part, not the 18. That just tells us that we were around the circle 18 times. What we're interested in is where we landed on. Where did we end up after going around 18 times? Well, this says that the remainder, that capital R notation, stands for remainder. You'd see that in a, I don't know, number theory class. You'd see that in an arithmetic class. The last time you've seen that big R notation, maybe elementary school. But that says that the remainder is 0, and that's all I'm interested in. I'm interested in the fact that this is the same as I to the 0th power, and we accept I into the world of numbers because it gives us exactly what we expect. I to the 0th power is 1. So I to the 72nd power, let's summarize what we just said here. I to the 72nd power is 1. So that's just another way of writing 1, which is kind of cool and shows that I behaves very much like we expect it to, like it should if it behaves like other numbers. So we're going to do 3 more of these, and they're going to be exactly the same. We're going to divide the exponent by 4 and see what we get. So here's I to the 59th. We're taking that 59, we're dividing it by 4. Okay, it goes around 14 times. Not interested in that. The remainder is 3. Well, that's where we end up. So this tells us that we've got the same number as I to the 3rd power. Now, I to the 3rd power takes us from I to the 0 is 1, I to the 1st is I squared is -1. You can rederive this in your head really easily, or you can just memorize the pattern. I cubed is -I. Okay, and around we go. 2 more examples, same kind of thing. I'm going to take that 126, I'm going to divide it by 4. I learned that I go around 31 times, and then 2 more. And it's the 2 more that I'm interested in. So that will tell me that this I to the 126th is the same thing as I squared, which is, by definition, -1. So we're doing really good. A silly question, you can probably do this in your head, so, and I do mean that. So if you want to just take a second to pause the video and take a look at I to the 4001, it's pretty clear to see what the remainder is when you divide 4001 by 4. That 4,000 is just telling us we went around 1,000 times, and the remainder is 1. So, and remember, you can do this in your head. That's I to the 1st power, which is just I. Okay, let's see the arithmetic. So we're going to take the exponent. We're going to divide it by 4. Yep, it went around 1,000 times. And we don't care about how many times it went around. We care about where it stops. Well, 1 more past that. So I to the 1st power, we just take the remainder and raise I to that power. And I behaves like every other number in this regard. I to the 1st power is itself. So when you look at this, this is saying, rightly, correctly, that I to the 4001 power is just I. In other words, that 4000 part of the 4001 just took us around that circle, around the clock face, if you will, 1,000 times. It was the remainder of 1 that was interesting to us. And with that, let me remind you that on this page, the big deal was the conjugate. So when you're going back and working through your homework and you see a conjugate question, remind yourself how that goes. You know it's a conjugate question when there's a sum or difference involving an I in the denominator. So you're going to multiply by the other one. If you've got a sum, you multiply by a difference. If you've got a difference, like in this example, you multiply by a sum. Okay, thanks so much. Have a good luck with your homework. Get in touch, use the forums if you need them, and be safe.